So yeah, welcome everybody to the, I guess it's called the Wednesday evening session, but I can see that for our speaker, it is not Wednesday evening. So we are privileged here from Arjun Ranganathan. I hope I said that correctly. He is at the Indian Institute for Science Education and Research, but I think he's currently at the University of Bordeaux on internship, and we are going to be learning about maximum running time of Hypergraph, Bootstrap, Percolation. So I'll hand it over to Arjun.
Thank you so much, Christian, for the intro, and thanks to everyone in the audience for showing up. Also, a big shout out to the organizers for the symposium. It's been great. So yep, as he said, today I'm going to talk about the maximum running time of Hypergraph Bootstrap Percolation. All of what I present today is based on joint work with Jonathan Noel of the University of Victoria. So first, I'd like to give you a broad overview of my plan for the talk today. So I'm going to start with a simple introduction to what Bootstrap Percolation really is, Bootstrap Percolation and Hypergraphs is. We're going to begin by looking at the case of a small hypergraph. We'll then see how to step up to bigger hypergraphs, use what we saw to look at a slightly bigger hypergraph, and then we tie it all together to present two really nice results that use everything, and we end with a couple of open problems. So yeah, let's begin with some preliminary definitions. So a hypergraph H consists of a pair of sets, a vertex set V of H and a hyperedge set E of H, which is a family of subsets of V of H. So every hyperedge is just a collection of vertices, a set of vertices. A hypergraph H is said to be R uniform if all of its hyperedges consist of exactly R vertices, and in this case we say that the uniformity of H is R. So for instance, a graph is just a two uniform hypergraph because in a graph every edge consists of exactly two vertices. The R uniform complete hypergraph of order K, which we denote K sub K superscript R, is the R uniform hypergraph on K vertices whose hyperedge set consists of all the R element subsets of the vertex set. So you have K vertices and every set of R vertices is a hyperedge. Now we define Bootstrap Percolation. So given an R uniform hypergraph F, the F bootstrap process, or simply the F process, starts with an R uniform hypergraph H naught. And then at every time step t at least one, the hypergraph HT is defined to contain all the hyperedges of HT minus 1, as well as every R uniform hyperedge E that completes a copy of F in HT minus 1. So that is to say that you add every edge E in HT minus 1 such that if you were to include if you were to include E in HT minus 1, then it creates a new copy of F that was not present initially in HT minus 1, and you add all such edges E to your new hypergraph HT. So here's a simple example of K3 bootstrap percolation. K3 is just a complete graph on three vertices, the triangle. So you start with H naught over here on four vertices and three edges in this example. So in H1, we add the edges AD and BC. So we add AD to complete the triangle ABD, and we add BC to complete the triangle BCD. In step 2 in H2, we add the edge AC to complete the triangle ABC or even the triangle ADC. The hypergraph H naught is referred to as the initial infection, and for time t at least 0, the hyperedges of HT is said to be infected at time t. The running time for a KKR bootstrap process with initial infection H naught is denoted MKR of H naught, and it's defined to be the minimum time t for which HT equals HT plus 1. So this is the smallest time t for which there is no hyperedge E that you can add to HT to create a new copy of a KKR. And so the process terminates, it stabilizes at this time t. The maximum running time among all hypergraphs H0 on n vertices is denoted MKR of n. So MKR of n is just the maximum overall MKR of H0, where H0 has n vertices. And in the case of graphs where the uniformity is 2, we often omit the superscript in all this notation. A key thing to observe is that MKR of n is at most n choose R, because if you have an R uniform hypergraph on n vertices, then it can have at most n choose R hyperedges. And since at least one hyperedge gets infected in each step, the maximum number of steps is at most n choose R, right? And consequently, MKR of n is big O n to the R asymptotically. The aim of the game really is to see when MKR of n attains this upper bound of n to the Rn. So this is primarily what we're going to be talking about today. So the running time in the case of complete graphs has been studied previously. And so here are some results. We know that for K3 percolation, M3n is logarithmic in n, M4n is linear in n. For M5n, we only have a lower bound that's almost quadratic in n. And M6n actually attains the upper bound of n squared and is big theta n squared. So now we will initiate the study of hypergraph bootstrap percolation for uniform hypergraphs, where the uniformity R is at least 3. So far we've seen graphs, now uniformity at least 3. And we start with the maximum running time of the K43 process. So to remind you, K43 is the 3 uniform hypergraph on 4 vertices whose hyperedge set consists of all 4 possible 3 uniform hyperedges on its vertex set. So K43 has 4 vertices, 4 hyperedges, each of which consists of 3 vertices. So we first look at a linear time K43 process for n at least 1 and distinct vertices v1 up to vn, u1 and u2. We define the beach ball hypergraph B of v1 to vn, u1, u2 to be the 3 uniform hypergraph whose vertex set consists of exactly these n plus 2 vertices. And so in this construction, we like to think of u1 here as the top vertex, u2 as the bottom vertex, and v1 to vn as a row of vertices in between u1 and u2. So the beach ball hypergraph has 3 types of hyperedges. You have the hyperedges of the form u1, vi plus 1 for I between 1 and n minus 1, which are shown in red here. So u1, v1, v2, u1, v2, v3, so on up to u1, vn minus 1, vn. Then you have hyperedges of the form u2, vi plus 1, which are shown in blue here. So u2, v1, v2, u2, v2, v3, so on. And finally, you have this green hyperedge u1, v1, u2, right? The idea behind the beach ball hypergraph construction is that the K43 process, whose initial infection is this beach ball, infects the vertical hyperedges of the form u1, vi, u2 sequentially one at a time. So let's go through this. So initially, this is what H0 looks like. And now you look at the K43 on the 4 vertices u1, v1, u2, and v2. So the top and bottom vertex and the first 2 vertices of your row. And as we can see, 3 of the 4 hyperedges are already there. This green one, u1, v1, u2, the blue one, u1, v1, v2, and the red one, u1, v1, v2. u2, v1, v2, and u1, v1, v2. And so as to complete the K43 on these 4 vertices, this green hyperedge, the one missing hyperedge from this K43, u1, v2, u2, gets infected in the first step, right? And now that this vertical hyperedge u1, v2, u2 is infected, that leads to the infection of u1, v3, u2 in the next step in the same manner, and so on until you finally infect u1, vn, u2 in step n minus 1, and you can show that the process terminates here. And now we just slightly modify this beach ball. So we define the augmented beach ball hypergraph B prime of v0 up to vn minus 1, u0, u1, which is obtained from the beach ball B of v0 up to vn minus 1, u0, u1 by adding precisely one hyperedge, and that's the hyperedge v0, u0, vn minus 1, which is shown in pink here. So you take the beach ball, you add this one pink hyperedge, and we call it an augmented beach ball. So the K43 process, whose initial infection is this augmented beach ball, proceeds in the same manner as the K43 process that starts on the beach ball up until step n-1. So to remind you, in step n-1, we infect this the last vertical edge u0 v n-1 u1, which is shown in yellow here. And now let's look at the K43 on these four bold vertices v0, u0, v n-1, u1. The hyper edges in the middle are still there. I've just not shown them in the figure so that it's easy to understand what's going on. Anyway, so if you look at the K43 on these four vertices, three of the four hyper edges are already there. This green one and this pink one were initially infected, and the yellow one got infected in step n-1. So to complete the K43 on these four vertices, the one remaining edge, the cyan colored edge, v0, u1, v n-1, gets infected in step n. So the K43 process on the augmented beach ball runs for exactly n steps. And now here's what we want to do. We want to chain together theta n number of augmented beach balls, each with running time linear in n, to get a K43 process whose overall running time is quadratic in n. And here's how we go about it. So let's say v0 up to vn-1 and u0 up to um-1 are n plus m distinct vertices of the initial infection h0. The ui's will be the top and bottom vertices, and the vi's will be the middle vertices of the augmented beach balls in our chain. The top and bottom vertex of the ith augmented beach ball will be ui-1 and ui respectively. So for the first augmented beach ball, the top and bottom vertex are u0 and u1. For the second one, they're u1 and u2 respectively. For the third one, you have u2 and u3, so on. And as we go from one augmented beach ball to the next, we will cycle through the order in which we have the middle vertices. So for the first one, the middle vertices are from left to right are in the order v0, v1, v2 up to vn-1. For the second one, we cycle through them once. So from left to right, you have vn-1, v0, v1, so on. For the third one, we cycle through them again. So from left to right, we have vn-2, vn-1, v0, and so on. And finally, we remove the first upper triangle hyperedge from all the augmented beach balls except the first one. So if you look at the second augmented beach ball, this hyperedge u1, vn-1, v0 has been removed. And in the third one, u2, vn-2, vn-1 has been removed, right? And so the idea is as follows. So let's say we start with h0 as the union. So our initial infection h0 is the union of all of these augmented beach balls. And now by construction, the K43 process on the first augmented beach ball is the only one that runs initially, because from the second augmented beach ball onwards, we've removed that one upper triangle hyperedge, which is needed to complete the K43 in the first step, all right? And so the K43 process can't run on the second or the third or the fourth beach ball because that hyperedge is missing. And so it runs only on the first one. And on the first one, the augmented beach ball hypergraph, the K43 process on this, it terminates with the infection of this pink hyperedge, v0, u1, vn-1. We saw this previously. It terminates with the infection of this lower side hyperedge. But this pink hyperedge is precisely the hyperedge that was removed from the second beach ball, because the one that was removed is v0, u1, vn-1. And so once this pink hyperedge gets infected, and in the nth step, so in the nth step of the first augmented beach ball, then it gets added to the second beach ball, and so this will trigger the second beach ball process, whose completion will then trigger the third one, whose completion triggers the fourth one, and so on. And yeah, so thus we see that the running time m43 of h0 is m-1 times n, because you have m-1 beach balls, each of which runs for n steps. And consequently, the maximum possible running time on m plus n vertices, m43 of m plus n, is at least m-1 times n. If you optimize for m and n, you see that m43 of n is at least quadratic in n, so it's big omega n squared. Now we see ways to step up to bigger hypergraphs. So we start with an easy step up lemma. So given an initial infection h0, for the KKR bootstrap process and a vertex W that is not a vertex of H0, there exists an initial infection H0 prime for the K plus 1R process whose vertex set consists of the vertex set of H0 along with W, such that both processes infect precisely the same hyperedges in every step and hence have the same running time. So for instance, we saw a construction of H0 for the K43 process. And what this is saying is there's a way to add a vertex and slightly modify H0 to make it a K53 process that infects the same hyperedges in every step, which you can then make a K63 process that proceeds in the same way and so on. And now a slightly harder step-up lemma. So let's say the uniformity R is at least 3. And if we're given an initial infection H0 for the KKR process that satisfies some nice properties, and we won't go into the details of these properties, there exists an initial infection H0 prime for the K plus 1, R plus 1 process. So both K and R go up by 1, whose running time is longer than that of the original KKR process by a factor of n. So if the original KKR process had running time t, the new K plus 1 R plus 1 process has running time n times t. So we saw that K43 has running time at least omega has running time omega n cubed. So I can show that K54 has running time, no, sorry, K43 has running time omega n squared. So I can show K54 has running time omega n cubed, K65 has running time omega n to the 4, and so on. You can step up like this. And we use this idea in a slightly bigger hypergraph, so we talk about this very quickly. So the key idea is that in a K53 process, I can transition from one beach ball to another, where the beach balls are modified using the easy step-up lemma to convert them from K43 to K53 processes. And how we do this, let's say I have two beach balls, B1 and B2, B1 on the left, B2 on the right, such that the last vertex of B1 and the first vertex of B2 on the middle row are the same. And suppose this cyan colored edge of B2 has been removed initially, so it doesn't run initially because this thing is missing. So only B1 runs initially, and B1 ends with the infection of this pink hyperedge that we saw. And I want to use this to trigger the infection of the cyan hyperedge on B2 in the next step. So if you look at the K53 on these 5 bold vertices, the 1, 2, 3, 4, and 5. So what we do, we initially infect every hyperedge of this K53 except this pink one and the cyan one. And so when B1 completes, it leads to the infection of this pink hyperedge. And so as to complete the K53 on these 5 bold vertices, the cyan hyperedge gets infected in the next step, and that triggers B2 and so on. So I can transition from one beach ball to the next. And we use this idea to construct an initial infection H0 on n vertices that consists of theta n squared beach balls, each with running time linear in n. And they're made to run consecutively such that the completion of one triggers only the next one. And so this shows that the maximum possible running time of a K53 process on n vertices, M53n, is at least of order n cubed. But because the uniformity is 3, we know that it's also big O n cubed. It's at most n cubed. And so M53n attains the upper bound and is theta n cubed, which is pretty cool. And now we quickly tie it all together and present 2 nice results. So we know that M43n is big omega n squared and M53n is big theta n cubed. And so these 2 facts along with the 2 step-up lemmas imply 2 nice results. So firstly, we see that R plus 1 R of n is big omega n to the R minus 1 for all R at least 3. And we talked a little bit about this because M43n is big omega n squared, M54n is big omega n cubed, M65n is big omega n to the 4, and so on. And the other thing is that MKRN is big theta n to the R. It attains the upper bound n to the R, which is what we really wanted. Right, so MKRN is big theta n to the R for all R at least 3, and for all K, that is at least R plus 2. And this also, if once you have that M53n is big theta n cube, you just repeatedly apply both the step-up lemmas, and that will directly imply this result. And finally, we present 2 open problems. So firstly, we'd like to know whether there is a non-trivial upper bound on the running time of the K43 bootstrap process. So we know that the K43 M43N is at least quadratic in N, and we conjecture that our quadratic lower bound is actually tight up to a constant factor. So we conjecture that M43N is big O of N squared. But so the other lower bound that we have is M R plus 1 R N is omega n to the R minus 1 for all R at least 3. So the special case of R equal to 3 is M43N. But we don't believe that this lower bound is tight for all R at least 3. And we ask whether for R sufficiently large, this mr plus 1r of n eventually attains the best possible upper bound of n to the r and becomes theta n to the r. And that has been my talk. Thank you so much for listening. And please let me know if you have any questions.
Perfect. Thank you. That was great. Yeah, are there any questions from anyone?
So yes, one question here. Thank you for the nice talk. I was wondering, you treat sequences of complete hypergraphs. Could your technique be extended to say sequences of hypergraphs that are included one in the other, but are not necessarily complete?
I don't know. So it's something that we only recently thought about, but it's our guess at least is that so perhaps the broad ideas can be used for things that are not complete, but the specific details in our proofs often use the fact that they are complete. But I can't say for, I have a feeling that at least the very broad ideas to some extent could generalize to hypergraphs that are not necessarily complete.
Okay, thank you.
Yep.
Okay, I see Jack has his hand up.
So I always forget the right language for this in hypergraphs, but you've always worked with the idea that it's totally fine to repeat edges in your when you put down triangles. What about
sorry, I didn't get that.
So like you're allowed to have two triangles, two edges of size 3 that share a pair of vertices.
Yep, that's allowed.
Yeah, has there been any research on hypergraphs where we don't allow that? I can't remember the word for what those are called.
I think those are called linear hypergraphs. I'm not too sure of this terminology
that sounds
either.
vaguely familiar, yeah.
Yeah, but honestly, I don't think there's been any research. So I don't know that there. So for the maximum running time question, at least I know that there hasn't been, but the framework of Bootstrap percolation presents lots of questions. For instance, you can ask, what's the minimum number of edges or hyper edges you need to infect such that eventually everything gets infected? And so you can ask a bunch of questions. So maybe in these other contexts, people have asked these questions, but for this particular question, I don't think anyone has. I could be wrong, but I don't think they have.
Cool. Okay. I could imagine as soon as you have that restriction, it's not even, you might end up with the case where the two edges that get infected in one step kind of violate that anyway.
Yep. Yeah. A lot of our constructions won't work in that once you have that restriction, right? And it also will greatly reduce the total number of hyper edges you're even allowed to have. So that feels like it would really reduce the running time.
Okay. Thank you.
Yep. No worries.
I have one quick question. I think we have like 30 seconds left. So yeah, I'm not a graph theorist by any means, but do you know if anything's been done to like on the actual computational side? So like developing algorithms to quickly compute each of these steps non-trivially, aside from just like checking each edge.
Sorry, what exactly do you want the algorithm to do? I didn't get that.
So like, I guess if I wanted a computer to compute each of these steps, I could just tell it to like, if it has a graph, like check every edge I could add, but there's probably a more efficient way to do it. Do you know if anything?
Yeah. So actually, when we were working on this, so I know nothing about computers, but the guy I've been working with, John, knows a lot. And so I don't know the details, but I think it was Adam Wagner of Tel Aviv, who I think last year posted this paper up on how you can use machine learning tools to come up with nice examples and counterexamples in combinatorics. And so what John did is that he used his computer to whip up some examples of initial infections that would run for really long, which was the hope, right? And the computer beat us is why we started to improve. And now it looks like we're doing at least as well as the computer. But in that sense, yeah, so there are better ways to come up with examples of processes that run for really long than, you know, brute forcing and trying every possibility. But this feels very new. So yeah, this is the limit of my knowledge when it comes to this.
Okay, yeah, cool. Thank you. Yep,
Yep.
that answered my question. Okay, well, yeah, let's all thank Arjun one more time. That was great. Yeah, thank you.
Thank you.